Hello folks, so this is my second video looking at hypothesis testing for the proportion of a binomial distribution. Follows on from the first video there about what a hypothesis test is. And we're going to look at one of the two methods of doing hypothesis tests. This one uses what we call critical regions. In the first video, we were introduced to this situation where I'd got a spinner with 4 different colours on, and it was spun 20 times, and the green came up twice, if you remember. And obviously, we might assume that the spinner is a fair spinner, so the probability of each colour would be a quarter, but we might have reason to believe that perhaps it's biased against green. For example, if a green has only come up twice, we might believe that it's biased against getting green. So we might want to do a hypothesis test to test that. And here we've been given a 5% significance level. You'll usually be given the significance level. If you're not, just use 5%. And we're going to use that significance level to do a hypothesis test on that theory. So, if you remember, we had this idea of a random variable. In this example, the random variable is the number of green results, the number of times that we spin a green. And then we have our null hypothesis and our alternative hypothesis. The null hypothesis, we said, was kind of the default state. So in this situation, we would assume that the spinner is fair, that the probability of getting a green is a quarter. What we're testing is whether it's biased against getting a green. So our alternative hypothesis, H1, is that the probability of getting our random variable, the probability of getting a green, is less than a quarter. And we always have to write those down. We then always assume that the null hypothesis is true, because that's the default state. In this situation, we've got a binomial because the spinner can either give us a green or not a green, and it fulfills all the other criteria for a binomial as well. You might want to go back and check the criteria for a binomial distribution and just check that you're happy that it fulfills those. So we looked at this graph that showed the probabilities of getting different values of our random variable, the probabilities of getting different numbers of green from our spinner when we spin it 20 times. We said that we'd expect to get 5, so that's the highest probability, and as we get further and further away from 5, the probability reduces. In this situation, what we're looking for is the probabilities of these values to be less than our significance level, less than 0.05, 5%. And we want to find a critical region where those probabilities do indeed add up to less than 0.05. So we're looking for a value of little x where the probability of x being less than or equal to that being less than 0.05. That value is sometimes known as the critical value. So let's see how this can be done on our NumWorks calculator. You've probably done similar things before, but it's good to have a recap. So the first thing we need to do is go into the distributions section because we're looking at the binomial distribution. So once you go into that, you obviously choose binomial. In the next screen, you can enter the number of trials. So in this case, we were spinning the spinner 20 times, and you put in the probability of success, which, assuming that the null hypothesis is true, was a quarter, so 0.25. Then on the next screen, you get something like this that's got the bars shown, similar to the diagram I've just shown. Again, we can see that 5 has the highest probability as we'd expect. You need to check that you're in the correct format. So here, our critical region is at the bottom end, the lower tail, if you like, of our distribution. So we need to make sure that we've got probability x is less than or equal to some value. The graph there, or the little diagram, that's actually a normal distribution, but it shows that tail to the left-hand side. What we need to do next is set the probability to our significance level. So our significance level was 5%, 0.05. So we put our probability in to that right-hand box. And then when you press equals, you should find that your calculator gives you this. It tells us that the probability of getting 2 or fewer greens is 0.09126043, and the number would carry on. The problem here is that we wanted our significance level, we wanted the probability to be less than our significance level. We wanted it to be less than 0.05. The numworks calculator always gives the probability that's just over 0.05. So what we need to do is change the value of little x from 2 to 1, because that will reduce the probability. And you can see once we've done that, we just dropped it from 2 to 1. You always just drop it by 1. We can now see that the probability is indeed less than 0.05. It is 0.0243, blah, blah, blah. So this is our critical region. The probability that x being less than or equal to 1 is our critical region. The actual significance level is the 0.0243, blah, blah, blah. So this screen just shows some instructions there written down. Just in case you struggle to follow that a bit, you might want to pause the video and just follow those instructions. But what we've actually found is that the probability that x was less than or equal to 1 was 0.0243, which is less than our significance level, and the probability that x was less than or equal to 2 was 0.0913, which is greater than 0.05. So we decided that that top one is the one we want, because the probability is below our significance level. Remember that that value there, the 1, is sometimes known as the critical value, and that probability, the probability of that, is our actual significance level. The critical region for this situation is that x is less than or equal to 1. So let's go back to how we were setting out our working. We'd written down our variable, we'd written down our null hypothesis and our alternative hypothesis, and we'd written down the distribution of x, assuming that the null hypothesis is true. What we then have to do is show that we've checked the probabilities either side of 0.05. So I just write down those two probabilities. And it's worth just showing that you recognize that the first one in this situation is less than 0.05 and the second one is more than 0.05. And from that, we can see that the critical region in this situation is x being less than or equal to 1. So if we go back to our test statistic, remember we spun the spinner 20 times and we can see that a green came up twice. So our test statistic for this example is that x equals 2. So what we can do is decide whether 2 is in the critical region. And 2 is clearly not, because the critical region is that the random variable x is less than or equal to 1, and we got 2. 2 is not in the critical region. And that tells us that there is insufficient evidence to reject the null hypothesis. The number of greens is not few enough to suggest that the spinner is biased against green. And we always have to put that in context as well. So I also add a sentence, there is insufficient evidence that the spinner is biased against green. So these are the steps. And it would be worth you looking at the first letters and perhaps trying to come up with some mnemonic which is going to help you remember all the steps in this process, because it is quite a long process. So just to recap, the first thing we do is state what the variable x represents. We then wrote down our two hypotheses using the correct notation. We assumed that the null hypothesis was true and wrote down the distribution of x given that assumption. We then used our calculator to find the critical region, making sure that we write both those probabilities down. We then look at our test statistic and decide whether it is in the critical region, and therefore decide whether there is evidence or not to reject the null hypothesis H0. And then we always have to write that conclusion in context. And that's doing a hypothesis test for the binomial using critical regions. Let's look at one more example. So here it says the local train is usually late 60% of the time. A new timetable is put in place and the company claims that it will be late less often. Out of the first 10 services of the new timetable, the train was late twice. Test the company's claim at the 5% level. So here our variable is going to be the number of times that the train was late. The hypotheses, well, the null hypothesis assumes that nothing's changed and therefore the probability that it's late is 0.6. Whereas what we're testing is whether the train is now late less often, i.e. the probability that it's late is less than 0.6. We assume that the null hypothesis is true and write down the distribution. In this case, it's a binomial distribution. We're looking at 10 services, so that's our n, and assuming that the null hypothesis is true, the probability of it being late is 0.6. We then use our calculator to work out the critical region. And if you pause the video and pop that distribution into the calculator, as shown before, you should find that it gives you the probability x is less than or equal to 3 is 0.0547, really close to 0.05, but still a little bit bigger. So we have to check the one beneath. Probability that x is less than or equal to 2, you should have found, was 0.0112. Therefore, our critical region for this situation is that x is less than or equal to 2. Next, we have to make a decision about the null hypothesis. Well, we're told that out of the first 10 services of the new timetable, the train was late twice. So our test statistic is 2. So is that in the critical region? Well, yes, 2 is clearly less than or equal to 2. So we can say that 2 is in the critical region, and in that situation, there is evidence to reject the null hypothesis. Remember, we always have to put that in context, so we can say that there is evidence in this situation that the train is late less often. And that's how you do a hypothesis test for the binomial using critical regions. Hope that was helpful, and you can try my other video on using the p-value method later on. Thanks, bye bye.